Okay, it's great to be back in ICTS and great to be at SpentaFest. Spenta has made a huge difference to, I think, all of at least the young people in the Indian string theory community, but certainly myself. The old people will have to say that themselves. Okay. I mean, maybe it's a bit of a stretch saying young for me, but we'll let this fiction continue. Okay. Okay. No, certainly for myself in many, many ways. Firstly, when I moved back to India after a stint in the US, Spenta did many things. One of the main things he did that I think was really important for me, and I see this only looking back, was that he made sure that young people like myself faced none of the hassle, none of the nonsense that people often end up facing in many institutions in India and around the world. Spenta sort of protected us in this perfect way, so perfectly that for a long time I didn't even realize I was being protected. It's only after many years later when I've grown less young and especially after Spenta left Mumbai that I realized how much he was actually doing to shield us from the nonsense. So the consequence of this, one of the consequences of this was that when I reached India, in TIFR, I feel I had as good a working environment as anywhere in the world, as Harvard, as Princeton, anywhere in the world. Fantastic colleagues, just room to do what you wanted, a wonderful intellectual supportive environment, and no nonsense. And I now say that was almost entirely Spenta, and it's a fantastic thing, and I'd really like to thank you for it. Spenta was, of course, really important to me also as a colleague. It's always been great discussing physics with him. It's always been great to talk to him about various things. I've collaborated with him on several occasions. And there are so many, and he's been very important to me and to all of us as a friend. But I can't go on about this because the 22.34 minutes left, so let's continue. Okay. I had a changer at some point. Okay. In my pocket. Okay. So my talk today is titled Black Hole Dynamics as Large D. It's based on several papers I've written over the last year and a half with collaborators, and the paper and work, important work, early work and ongoing work done by Emparan, Suzuki, and Tanabe and collaborators. So, in this talk, I'm going to study the classical dynamics of objects that have always fascinated Spenta, and these objects are black holes. Now, classical black hole dynamics, you might think is a 100-year-old solved problem, because it's governed by equations that were written down 100 years ago by Einstein and Maxwell, if you include charge. You might wonder what there is to study about this problem. You see, this is often the way it is in physics. You write down some equations and the story is in principle complete, like QCD. The Lagrangian of QCD defines the theory. But then to extract the physics from that is not always very easy. That's the situation with black hole, with the dynamics of black holes. In situations where the black holes are very dynamical, black hole dynamics can be very complicated, even though the underlying equations that govern this dynamics is very well known and quite easy to write down. So what I'm going to try to do is to find some sort of simplification in black hole dynamics. A way of viewing black hole dynamics that is different from the usual way, but is still correct. In order to do that, I do what we often do. I change the problem. Instead of studying the dynamics of black holes in 4 dimensions, as you would be interested in if you were a LIGO experimentalist, I study the dynamics of black holes in d dimensions, and then take d to be very large. While everything I'm going to be doing is very different in detail from what I'm going to say next, the spirit of this maneuver is very similar to the spirit of the maneuver used to move to the 1/n expansion that Spenta has used so effectively for over 35 years in the study of gauge theories, matrix models, and quite interestingly also black holes, though that's another story. Okay, so now this is a short talk. It's 20 minutes to go. And I will not have the time even to outline any derivations of any of the statements I'm going to make. I'm just going to state our main results and try to explain their consequences. Okay, so let's start by stating the results. In the limit of a large number of dimensions, and under certain conditions, and I'll explain that a little bit, it turns out that the classical dynamics of a black hole is equivalent or dual to the following non-gravitational problem. This is the non-gravitational problem. Consider flat non-gravitational space-time, Minkowski space. Okay? Except that you take one or more holes eaten out of the space-time. Okay? Actually, I should have called these holes tubes, because they're holes in a constant spatial slice, but then they move in time. Okay? So one or more holy tubes eaten out of space-time. Okay? The boundary of these holes, I'll just continue to call them holes, the tubes. The boundary of these holes is a codimension 1 surface, which I'm going to call the membrane. The shape of this membrane is dynamical, because it's the boundary of this hole, whose shape wiggles around. Okay? In addition, so this is one of the dynamical degrees of freedom of the membrane. In addition, the membrane carries a charge field on its boundary and a world volume velocity field. By a world volume velocity field, I mean a velocity field tangent to the direction of the boundary. Of course, it also moves because its shape is changing, but that's normal to the boundary. It also carries a velocity field tangent to the boundary. Okay? Now, so I'm just continuing a statement of this auxiliary problem, which is equivalent to black hole dynamics at large D. The membrane carries these fields. Out of these fields are built the basic quantities that define the dynamics of the membrane. Okay? And these basic quantities are a charge current and a stress tensor that lives on the world volume of the membrane. So the membrane carries a charge current and a stress tensor, and the charge current and stress tensor are functions of the charge, shape, and charge density, the shape, charge density, and velocity field on the membrane. These functions are local functions of the local membrane variables, of the shape variables, the velocity, and the charge field. And at leading and first subleading order 1 over d, they're given by these formulas. The stress tensor is given in terms of this velocity field UA. The extrinsic curvature of the membrane surface, viewed as an extrinsic curvature of the surface embedded as a submanifold in flat spacetime, and the trace of this extrinsic curvature, this trace kappa. Okay, it's given by some formula here. We won't have time to look at these formulas in too much detail in this talk, but those of you who are familiar with hydrodynamics will see several hydrodynamical looking expressions here. This is a shear tensor, for instance. This is very much like the stress tensor of a collection of a pressure-free fluid. And there are various other terms we could try to recognize as we went along. In addition, apart from the stress tensor, the membrane carries a charge current. Part of the charge current is just that there's charge being carried along by a velocity. And then there are other terms, including Fick's law kind of term, charge current proportional to derivative of Q. Okay. So we've got degrees of freedom on this boundary. Out of these degrees of freedom are built a stress tensor and a charge current. Now, one of the really important things about the stress tensor and the charge current is that it's conserved, that both these fields are conserved. Okay? So this stress tensor obeys the equation del dot t is equal to 0, and the charge current obeys the equation del dot j is equal to 0. And if you just work out those conservation laws for these expressions and keep the relevant orders in 1 by d, the stress tensor conservation turns out to be this plus this equation. This is the stress tensor conservation in the direction of u, and this is the stress tensor conservation orthogonal to u. This P is a projector orthogonal to u on the world volume of the membrane. And this is the charge conservation equation. Okay? So, if you just work out these conservation equations, you get these equations, which turn into dynamical equations of the fields of the problem. The fields of the problem are the shape of the membrane, the velocity field, and the charge density field of the membrane. Now, something that's really important here is that if you do the counting, okay, if you do the counting, you'll find that there are totally d equations. Okay, why are there d equations? Stress tensor conservation has as as many free indices as the manifold you're on, but we're on a codimension 1 manifold, so that's d minus 1 equations. And charge conservation is scalar equations, so that's d equations. But the number of variables in the problem also is d. The variables are a shape function, that's 1, a charge function, that's another, that's 2, and a velocity field. So velocity field is a vector field in d minus 1 dimensions, but it obeys u square equals minus 1. So that's d minus 2 variables. So 2 plus d minus 2, that's d. So these conservation equations give you as many equations as there were variables on this membrane problem, and so define, or at least plausibly define, a good initial value problem for the variables on a membrane. Okay, so these conservation equations determine the dynamics of these bubbles or these holes eaten out of space-time. You give me the initial values of the variables on the membrane, I can tell you what they are at later times if I'm good at solving differential equations. Okay, now everything I've told you about was at leading order in 1 by d, but this expansion can be systematically carried out to all orders of the 1 by d expansion. Just to convince you I'm not bluffing, I've quoted the next order correction to the equation of motion, the first sub-leading correction to the equation of motion in this transparency. That comes from a sub-leading correction to the stress tensor. That was just an existence proof. Okay. So I've told you that the motion of black holes is dual to the strange problem. You look at holes eaten out of a flat space-time, you look at these holes evolving in time, and all the evolution happens on the boundary with these membrane degrees of freedom. Now I want to tell you a little more about how this problem maps to the black hole problem we were really interested in. Kappa is trace of K, trace of the extrinsic curvature. Okay, now, as we said, each solution to the equations of motion I wrote down for you in the previous transparency describes some motion of a bunch of holes moving around in flat space-time. Now, each such motion is dual to the dynamics of a collection of black holes at large d. The number of holes is the number of black holes. And the duality works under 2 conditions. The first condition is that the surface of my membrane is not crumpled up on a length scale that involves 1 by d. Okay? It's smooth on length scales order unit. The second condition is that the membrane does not vary in too many directions simultaneously. Okay? It doesn't vary in order d directions simultaneously. It's a bit harder to make this precise in the time I have in this talk, but I just comment that one way to satisfy this condition is to preserve an SO d minus p minus 3 isometry in our solution and keep p fixed as I take d to infinity. There are many other ways to preserve this condition. This is one concrete way. Okay, now under these conditions, these holes map I've set to black holes. The inside of the hole, the part that's not there in our flat space-time, maps to the interior of the black hole. The surface of the hole, the membrane, maps to the event horizon of the black hole. And the exterior of the hole maps to the exterior space-time. Okay, now I want to say this in a little more detail. Let rho give you a measure, and some rough measure. We have a precisely in our papers, but some rough measure of the distance from the membrane on the outside. Okay? If I want to actually construct the black hole metric dual to this membrane solution, what I have to do is the following. It turns out I have to solve 2 different problems. When rho by R naught, where R naught is the local radius of the local Schwarzschild black hole at the given point on the membrane, some effective length scale of that solution. When rho by R naught is much, much larger than 1 by d, when in some natural unit you're away from the membrane by a distance that's large compared to 1 by d. Okay? Then the space-time metric for the black hole solution dual to our membrane configuration turns out, and I'll explain this a little more as we go on, turns out to be effectively flat space perturbed by a very small correction. Therefore can be described by a linearized solution of Einstein gravity. And the linearized solution is given in a very simple way. It's given by taking the stress tensor on the membrane and convoluting it against the usual kinds of Green's function. That gives you a linearized solution of Einstein gravity, a retarded Green's function. That's the correct solution that reproduces the exterior of the actual black hole. This is good only when rho by R naught is much, much larger than 1 by d. On the other hand, when rho by R naught is much, much less than 1, there is the deviation of the metric away from the flat space metric is not small, but another approximation takes over. Okay? Instead, the simplification happens now by the fact that the deviation, while not small, turns out to be local. That is, locally determined by the membrane variables of the membrane near where you're expanding. Okay? So locally determined by the membrane shape, velocity, field, and charge density. In this region, we can explicitly solve for the metric in terms of the membrane variables. In our papers, we have huge formulas determining the metric. Okay, very explicit formulas. Okay? And the important simplification here is that it's local. Far away, it's not local, but it's linear. Nearby, it's not linear, but it's local. In this region, both approximations apply. The solution is both linear as well as local. Okay? And where both approximations apply, the two approximations give the same answer. Okay. Now, it's very important that the metric deviates significantly away from that of flat space in a shell of thickness 1 by d around the black hole. It does not when you go to large distances, large compared to 1 by d away from the black hole. Okay? But this is very important. So the metric very near to the membrane is not that of flat space. In particular, it turns out that the membrane world volume, which is time-like when viewed as a submanifold of flat space, is null when viewed as a submanifold of the true metric, okay, of the black hole. And this, of course, had to be, if you were paying attention to what I was saying, because I told you that this membrane world volume was an event horizon of the true metric. The event horizon is always null. But remember, in the auxiliary problem, the membrane world volume is time-like. In the true metric, it's null. But the equations of motion we always solve are just of the auxiliary problem. So for the auxiliary problem, it's just like a soap bubble. Okay? So it's a duality going on. Either you consider gravity or you don't. In the problem where you don't consider gravity, there's no null surface, just an ordinary soap bubble type surface. Okay, now I want to tell you a little bit about why it was that the metric became so small when we went to distances large compared to 1 by d away from the membrane. This might at first sight seem strange to you, given the fact that the stress tensor that I quoted to you, or the charge current I quoted to you, is not small. In fact, in natural normalizations, these turn out to be of order d. They're quite large in the large d limit. So why is it true that you've got these large stress tensors, and yet I tell you that when you go to distances large compared to 1 by d away from the membrane, the response of gravity to these things becomes small. And the reason for that is very simple. It turns out to just be kinematical. Just a simple kinematical fact about Green's functions in large dimensions. Something very simple, but something I hadn't appreciated before looking at this. So in order to understand that, let's do the following. Let's try to solve for the Green's function of the operator del square, just a scalar Green's function. Okay? We work in radial polar coordinates and do a slightly strange thing. We work in Fourier space and time and position space and space. It's a bit strange, but it helps bring out the features of the problem very nicely. When you do this, the Green's function is defined in terms of an auxiliary function psi, which obeys a Schrodinger type equation. And the Schrodinger type equation is the equation of a particle moving in a potential that's given here, and with energy omega. The important thing about this potential is that it's huge at r of order unity. It's d squared by r squared. So it's order d squared when r is order unity. Okay? Whereas, if you're interested in things happening at timescale unity, omega is order 1, your energy is very small. So in order to solve for this Green's function, what you have to do is to look at the Schrodinger problem tunneling through a huge potential. Because the potential is so large, square root v is order d, and once you go a distance 1 by d, you start decaying exponentially very rapidly. Okay? So the smallness of the perturbation when you go to large distances compared to 1 by d is simply a consequence of this Green's function, kinematical consequence of this Green's function at large d. In fact, we can say more. You see, this decay continues until this energy becomes equal, until the energy becomes equal to this, which you can easily see happens at r is equal to d by 2 omega. Okay? So this decay continues for a very long way. After this decay ends, the solution starts oscillating and becomes what we would think of as radiation. Okay? because the decay continues for such a long way, radiation is very highly suppressed in these things. Turns out that radiation occurs at order 1 over d to the power d. Okay? It's a huge potential and you have to tunnel very far. Okay. Note that everything I said is correct only when omega is order unity. When omega is order d, there is no suppression for this problem. Oh, the potential is not effective in suppressing radiation fibers. Okay. Fine. Now the fact that the interior of the black hole is simply a hole in space-time is a reflection of a well-known fact in general relativity, an obvious thing. The reflection of the fact that the inside of a black hole doesn't affect the outside because it's a causal boundary. And so from the point of view of trying to predict the outside, you can just replace the inside of the black hole by whatever you want. It's just a hole. Okay? That is, of course, something obvious. The important thing in what we've done, important thing in large D, is that the outside of the black hole is non-trivial only over a region that's very thin, order 1 over d. And so can be effectively replaced by a local system. And that, a local infinitely thin system, and that local infinitely thin system is our membrane whose equations of motion I've talked to you about. There's a sense in which there are light degrees of freedom living here, and light degrees of freedom living outside. Light degrees of freedom living outside are the modes that you can radiate away. Light degrees of freedom living here are the modes of the membrane. The two hardly talk to each other. In fact, they are more or less decoupled. Decoupling is violated only at order 1 over d to the power d, and the lack of decoupling is in fact radiation. Okay, now the simplest membrane solutions are spheres. It's easy to see that this just spherical static membrane is a solution. These are, of course, dual to static charged black holes. Once you have the spherical membrane solution, you can linearize the equations of motion around it. Okay? This linearization is easy to do, and you find a bunch of frequencies. I don't have the time to go through these frequencies in detail with you. The two things I want to tell you about them are the following. First, apart from a set of easily identifiable exact zero modes, translation, boosts, rotations, these modes are all dissipative, and dissipative at leading order. The dissipation doesn't start at first subleading order 1 by d. So these equations, our membrane equations, are as dissipative, in fact more dissipative than those of hydrodynamics. More dissipative because hydrodynamics becomes dissipative only at first subleading order in the hydrodynamic equation. Perfect fluid hydrodynamics is non-dissipative. There's no such thing as a perfect membrane equation. The membrane equation is always very dissipative. Okay? And you can make this more precise by taking our membranes and showing that they have an entropy current that lives in them. The entropy current is actually calculated by just taking the area form on the event horizon of the true solution and uplifting it to the membrane. And Hawking's area increase theorem guarantees that this entropy current is always positive divergence. In the particular case of the membrane, you can work this out carefully and show that that there's a particular entropy current, which is basically just the velocity. The divergence of the entropy current is something positive definite, and the positive definite thing is shear square. Okay. Again, an equation that looks very much like hydrodynamics for those who are familiar with this. So the fact that this entropy is always created and never destroyed locally is a local form of the second law of thermodynamics, and is connected with the dissipative nature of these membrane equations. Now, I've looked at one kind of solution. Another kind of solution is, there's another kind of sort of interesting similar solution you can look at. A solution which is a sphere times let's say, r or r to the power p. These solutions are sometimes in the general relativity community called black brain solutions. Okay, and they're well known to suffer from certain instabilities, the so-called Gregory Laflamme instabilities. You can check that our membrane you can take our membrane equations, linearize them around these solutions, and find, it turns out that one of the modes that was a zero mode without this extra direction, whereas momentum along this extra direction becomes a non-zero mode, and picks up an imaginary part of the form that corresponds to an instability. Okay. It's an IR instability, so it's an instability unless the momentum is very large. Okay. And you can also check that there is a certain scaling limit of these membrane equations that captures this instability and captures it in a nonlinear fashion, also captures the endpoint of this instability. At this point, yes, 3 minutes. Okay, at this point, these nonlinear equations agree with a set of nonlinear equations determined by Emperan, Suzuki, and Tanabe about a year ago, using completely different techniques, using quite different techniques. And we now understand that the Emperan, Suzuki, Tanabe black brane solutions are basically a scaling limit of our membrane solutions. Okay, you can easily find stationary solutions, nonlinear stationary solutions of our membrane equations. They correspond to these holes which are ellipsoidal, rotating around, okay, puffed out by a centrifugal force. In fact, I think that nobody's really tried this carefully, but I think that it might be possible to classify all stationary solutions of black holes at large D, because these membrane equations become really simple when they're stationary. Okay, I've so far talked about these holes moving around in flat space, but this is a simple generalization. Suppose you've got any vacuum solution of Einstein's equations, for instance, a long wavelength graviton. You want to study a black hole moving in that background. All you have to do is study holes eaten out of that solution. Okay? The membrane is a membrane that lives in this solution, and its equations of motion are basically the same, to first order 1 by D, basically the same as the equations of motion I wrote down to you, just by the equivalence principle. You just promote every derivative to a covariant derivative. Okay? So using this, you can, at large D, study questions like, if you've got a gravity wave incident on a black hole, how does it respond? What are the polarizabilities of black holes? What is you can calculate sort of black hole refractive indices in some sense. And there are interesting formulas that I don't have the time to tell you about. This is the last thing. That. Okay. So far I've considered this formal system quite in certain configurations. But now we get to something that's really interesting. And the really interesting thing is this. Suppose you have two of these holes, two black holes, two of these holes eaten out of flat space, and they come and bang into each other. Can we now understand what's going on at large D? Well, there is a region of this bang where we don't control so far. And that region is when these two holes come to within a distance 1 by D of each other. In this region, our approximations break down. It's not just the approximations breaking down is not just a technical thing, it's probably a physical thing. Because for a while here, the time scales involved are of order 1 by D. And as I told you, the suppression of radiation, which happens at omegas of order 1, is not there when omegas order 1 by D. So it seems very plausible that for a time, you will see a flash of radiation emitted very strongly. Okay? This is unfortunately happening when our approximations break down. We're hoping that we can find a new approximation to govern exactly what happens here. This is a very important problem because it seems to me very likely that the main thing you would see if you were a large D observer looking at two black holes colliding is a flash whose time is of order 1 by D. If we could predict that, that would be really great. And then you would see a very small tail afterwards, which we can already predict. But it would be very nice to understand that. We're not yet there. Okay, there are future directions, the conclusions. I'll stop here. Okay, thank you.
If you take the long wavelength limit?
Well, we need to take a long wavelength with respect to something. If you've got a membrane which is a sphere, you can't take the wavelength to be larger than the radius of that sphere because there's no place for it to be. Okay, so the membrane equations in some sense are long wavelength compared to the other natural length scale in the problem, which is 1 by D. Now, if you want to take a longer wavelength, you've got to be in a situation where you've got a black brane. Okay? This is related to what I was telling you about for this Gregory Laflamme transition, but would be more closely related if you took the story that I've told you about and generalized it to ADS space. Okay? Then you would have these large D black branes. This is something Shantany and collaborators have more or less done. And Emperan and collaborators also have some papers on. The basic expectation is that in that context, you would recover the large D equations of hydrodynamics, okay, but more. And the basic idea there is the following. See, you might think that this is a very different picture, but it's not. See, in fluid gravity, the degrees of freedom of the fluid are velocity and its temperature. But when you geometrize that temperature, it becomes the height of the event horizon. So that maps in this membrane language to the velocity of the membrane and the height of the membrane. So that's the shape of the membrane. So you see, that's roughly how it works. There's more to say about it later.
So if I recall your equations, they are some sort of a projected version of just the standard Navier-Stokes type of equations, right?
Plus with forcing terms having to do with curvatures that are absent.
Is there an equation for that? That's what I wanted to know.
Is there an equation for?
For this curly K.
Yes. Okay, good. So curly K by itself is not a variable. The variable is the shape of the problem. The shape of the membrane. Yeah, so there's one degree of freedom which is the shape, and that determines K. Okay? So there are as many equations here as variables, but only if you count the variable as the shape. You know, you shouldn't think of K as independent variable.
So K is a function of
the shape.
Of U?
No, of the shape.
The shape.
You see, because K is just the extrinsic curvature. So K is just a symmetric derivative of the normal to the surface, projected orthogonal to the surface. So if you know the surface, that is, if you know the shape, you know K. Yeah, but it's not obvious from this point of view, but these equations do give you an effective equation for the shape, and therefore for K.
So time to move on. Thanks very much, Shiraz.